Imagine a computer performing a calculation in minutes that would take a conventional machine an incomprehensibly long time to reproduce. That is the extraordinary idea behind Google's Willow quantum processor. Willow is a 105-qubit superconducting quantum processor developed to explore a fundamentally different approach to computation. Unlike ordinary computers, which process information using bits represented as zeros and ones, quantum computers use qubits that can occupy quantum superpositions and become entangled with one another. This difference allows a quantum processor to manipulate information in ways that have no straightforward classical equivalent. One of the demonstrations associated with Willow involved random circuit sampling, a specialized benchmark designed to test how effectively a quantum processor can execute and sample the results of highly complex quantum circuits. The reported comparison was staggering. A task completed by Willow in minutes was estimated to require an extraordinarily long time for a classical supercomputer using conventional simulation approaches. But there is an important detail. Random circuit sampling is not a normal application such as writing software, searching the internet, or solving a medical problem. It is a carefully designed benchmark intended to expose the computational difficulty of simulating certain quantum systems with classical machines. That distinction matters. Quantum computing is not simply about making every calculation faster. Instead, the goal is to develop machines capable of solving particular classes of problems in ways that classical computers struggle to reproduce efficiently. The reason this becomes possible begins with quantum mechanics. A classical bit must be either 0 or 1. A qubit can exist in a combination of quantum states before measurement. When multiple qubits become entangled, the mathematical description of the entire system becomes extraordinarily complex. For 105 qubits, the full computational state space contains up to 2 to the power of 105 basis states. That is an enormous number. However, this does not mean a quantum computer literally stores a separate classical copy of every possible state, nor does it mean the processor contains more physical information than the universe. Instead, the quantum system is described by a wave function whose amplitudes encode probabilities for different outcomes. The real challenge is controlling that quantum state accurately. And that leads to one of the biggest problems in quantum computing. Qubits are fragile. Heat, electromagnetic interference, microscopic vibrations, imperfections in hardware, and interactions with the surrounding environment can disturb quantum information. This process is known as decoherence. If errors accumulate faster than they can be corrected, a quantum calculation becomes useless. For years, researchers faced a frustrating problem. Adding more physical qubits could potentially increase computational capability, but it could also introduce more opportunities for errors. A useful quantum computer therefore requires much more than simply increasing the number of qubits. It needs reliable quantum error correction. This is where Google's Willow results attracted significant attention. The processor was designed to investigate whether increasing the size of a quantum error correcting system could actually reduce the logical error rate rather than making the situation worse. Demonstrating that trend is extremely important because scalable quantum computing depends on the ability to create logical qubits that are protected from the imperfections of individual physical qubits. This does not mean quantum computers have suddenly become fully fault-tolerant. They have not. Researchers still face enormous engineering challenges before large-scale practical quantum computers become reality. But progress in error correction could represent one of the most important steps toward that goal. The implications are potentially enormous. A sufficiently powerful and reliable quantum computer could eventually help scientists simulate complicated molecules, investigate new materials, study chemical reactions, and tackle problems that are extremely difficult for classical machines. Some researchers are also interested in applications involving optimization, cryptography, and physical simulation. But these possibilities remain future goals. The machines available today are still experimental and specialized. Their greatest value may currently be scientific. They allow researchers to investigate what happens when information itself is governed by quantum mechanics. And that leads to an even stranger question. What does quantum computing actually tell us about reality? The true challenge of quantum computing is not building a machine that can perform an impressive laboratory demonstration. The real challenge is building a system that can perform useful calculations reliably, repeatedly, and at a scale large enough to solve important problems. That requires fault tolerance. A fault-tolerant quantum computer would use many physical qubits to create more reliable logical qubits. Sophisticated error correction methods would continuously detect and correct certain types of errors without destroying the quantum information being processed. This is extraordinarily difficult. Every additional component introduces new engineering challenges. Researchers must maintain extremely low temperatures, control individual quantum states with precision, reduce unwanted interactions, and operate enormous numbers of components without allowing errors to overwhelm the calculation. That is why advances in error correction are so important. If logical error rates can continue decreasing as quantum systems become larger, researchers could eventually move toward machines capable of sustained, useful quantum computations. What might those machines actually do? One possibility is chemistry. Molecules obey quantum mechanics, which makes accurately simulating their behavior extremely demanding for conventional computers. A sufficiently capable quantum computer could potentially model molecular interactions more naturally, helping researchers investigate chemical reactions and materials. That could eventually contribute to the development of new catalysts, industrial chemicals, energy technologies, or pharmaceuticals. Another area is materials science. Scientists are interested in using quantum simulation to explore materials with unusual electrical, magnetic, or thermal properties. The long-term dream includes discovering materials that could improve energy storage, electronics, or other technologies. Optimization is another potential application. Many real-world systems involve enormous numbers of possible combinations. Scheduling, logistics, network design, and other optimization problems can become computationally difficult as their scale increases. Quantum algorithms may eventually provide advantages for some of these tasks. Cryptography is another major reason quantum computing receives so much attention. Powerful future quantum computers could threaten certain widely used public key cryptographic systems because algorithms such as Shor's algorithm can theoretically solve particular mathematical problems much more efficiently than known classical approaches. That is why researchers are developing post-quantum cryptography designed to remain secure against future quantum attacks. But there is a major caveat. The existence of Willow does not mean today's encryption systems have suddenly become obsolete. A cryptographically relevant quantum computer would require far more capable, fault-tolerant hardware than current experimental processors provide. The same caution applies to claims that quantum computing will immediately transform medicine, climate science, artificial intelligence, or the global economy. The potential is enormous. The practical timeline remains uncertain. And that uncertainty is part of the scientific story. Quantum computing is still a rapidly developing field, with competing architectures, error correction strategies, algorithms, and hardware designs. Google's Willow processor is therefore better understood as one important milestone in a much longer journey. Its significance is not that humanity has built a magical machine capable of solving every problem. It is that researchers are demonstrating increasingly sophisticated control over quantum information. That achievement brings us closer to a future in which quantum processors might perform calculations that classical computers cannot efficiently reproduce. And this is where the philosophical questions become especially interesting. Quantum mechanics already forces us to abandon many assumptions based on everyday experience. Particles can behave like waves. Systems can exist in superposition. Separated quantum systems can become entangled. Measurements can produce outcomes that cannot be predicted individually, even when the probabilities can be calculated with extraordinary accuracy. Quantum computing turns these strange principles into engineering tools. Instead of treating quantum behavior as something mysterious happening inside laboratories, researchers are learning how to manipulate it deliberately. The processor becomes a controlled experiment in the fundamental behavior of information and matter. Yet it is important not to confuse technological capability with an answer to the deepest philosophical questions. Will a quantum computer prove the multiverse? No. Will it demonstrate that human beings can communicate with parallel universes? There is currently no evidence for that. Will quantum computing replace classical computers? Almost certainly not in every application.